Okay, so we're going to look at these two examples. Now, unlike the examples that we looked at earlier, we are going to look at these which represents polyatomic ions, all right? The ones we saw earlier were simply molecules. And of course, polyatomic ions, because their ions carry a charge. So we're going to basically go through the same procedure, but there's a slight modification in order to take into account the fact that these structures carry a charge. So let me, okay, so basically these questions are asking, it's very simple. First, to write a plausible Lewis structure for the nitrate ion and do something similar for the carbonate ion. So what I'm going to do is go to my whiteboard here and start off with the nitrate ion. So the same process we begin with, we count up the number of valence electrons. So we go to the periodic table and we look up the group number for nitrogen and we see that it's 5. And we do the same thing for oxygen and we see that it's 6. But we have to multiply that by 3, so that gives you 18. Now, here is where there's a difference between what we did before and what we need to do now. We have to take into account the fact that we have a negative charge. So therefore, for every negative charge, we add 1 electron, all right? And therefore, that will be added to the total. So therefore, in this case, you're going to have 24 electrons total, and that will equal to 12 pairs, all right? So we do like what we did before. We put the nitrogen in the middle, and we surround it with the oxygens, since the nitrogen is a less electronegative element. And then we start with the bonding pairs. 1, 2, 3. So we have used 3 of the 12 pairs. Then 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we need to calculate the formal charge. Now remember, the formal charge formula is the group number minus half the number of bonding electrons minus the number of non-bonding electrons. So in the case of nitrogen, so let's do for nitrogen, the group number is 5 minus half the number of bonding electron, which is 2, 4, 6, minus the number of non-bonding electron, which is 0. So that gives you a total of 5 minus 3, so that will be plus 2. So the nitrogen atom will carry a plus 2 charge. All right? Then we do the same thing for each oxygen. So the formal charge of oxygen will be equal to the group number, which is 6, minus half the number of bonding electrons, which is 2, minus the number of non-bonding electrons, which is 6. So that will give you a charge of minus 1. So each oxygen atom will have a minus 1 charge. Okay, so if you remember what we did before, where we have an atom at the center with plus charges bonded to atoms with negative charges, remember we form multiple bonds in order to allow the charges, the positive and negative charges, to cancel out. Now, in this case here, obviously, we have a plus 2 charge here connected to atoms which each carries a negative charge. So therefore, we know that this pair of electrons will come here to form a double bond, all right? And therefore, this negative charge will cancel out one of these 2 plus charges. Now, I can totally understand at this point, based on what we have learned so far, that you might be tempted to do another similar movement of electrons from, let's say here, pair of electrons here, to form another double bond. But that would be incorrect. And the reason why is because of something we mentioned earlier. Let me see if I can find that slide. Okay, I can't seem to find it, but I remember mentioning it, that elements in periods 1 and 2 cannot have more than 8 electrons on their outer shell. Okay, I can't find the exact slide, but basically, the nitrogen, which belongs to period 2 in this case, cannot have more than 8 electrons on its outer shell, all right? So therefore, this will not happen. Let me make a note here. This here will not happen, all right? So therefore, you only have this pair of electrons coming here to form a double bond, and therefore the final answer, I'm just going to put it right here. The final answer is going to be O double bond N O minus O minus, and a plus charge here on the nitrogen. And that would be the final answer as far as the nitrate ion is concerned. Again, let me emphasize, nitrogen belongs to period 2. Nitrogen, therefore, cannot have more than 8 electrons on its outer shell. Only the elements beyond period 2, meaning period 3, 4, 5, 6, and 7, can have more than 8 electrons on their outer shell. All right? So that is something that you need to be aware of. So basically, that's the answer. All right, so the next example is the carbonate ion. Let me erase all this here. So in the case of the carbonate ion, carbon will have contributed 4 electrons on the valence shell. Each oxygen will contribute 6 electrons times 2. And because of the negative charge, we have to add 2 more electrons. All right, so 6 times 12 gives you, 6 times 2 gives you 12. 12 plus 2 gives you 14. 14 plus 4 gives you 18. So therefore, the grand total here would be 18 electrons, which would be equal to 9 pairs. 9 pairs. Okay, let me continue to erase this crap here. So, as we would have done before, we set up the arrangement of the atoms such that the carbon is in the middle, surrounded by the oxygens. We put the bonding pairs here, 2, 3. So we have used up 3 of the 9 pairs. 4, 5, 6, 7. Okay, I think I made a mistake here. Carbon is 4, 12. So 12 plus 4, 16, 18, 19. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, what's the mistake I made here? Oh, this should be 18. I knew I made a mistake here. Okay, so this is 18 electrons, so therefore this is incorrect. So this should be 24 electrons equal to 12 pairs. All right, okay. So now we have the electrons correctly distributed and accounted for. So what we need to do here is calculate the formal charges, just like we did before. So formal charge of carbon is going to be equal to 6, the group number minus half of 6, which is the number of bonding pairs minus 0. So this is going to give you plus 3. And for each oxygen, as we did before, its formal charge will be equal to 6 minus half of 2 minus 6 equals to minus 1. So the carbon will have a plus 3 charge. The oxygens each will have a minus 1 charge. And then we shift our electrons so that each negative charge will cancel each plus charge. And in this case, carbon will end up with a total of, let me see here. Actually, I made a mistake again. Sorry about that. Basically, the formal charge of carbon will be half of 6 minus half of 6 plus 3. Okay, where did I go wrong? Oh, okay. So again, I made the same mistake that I told you guys to avoid, because carbon cannot have more than 8 electrons on its outer shell. So basically, this is what happens, right? Only this pair of electrons will shift here. So therefore, the final answer for the carbonate ion Lewis structure is CO minus O minus, and in this case here, a double bond O and 2 lone pairs. So this here would be the final answer for the Lewis structure of the carbonate ion. So the only difference between what we did here in the case of polyatomic ions and what we did in the case of molecules is that we add electrons equal to the number of negative charges. Now, if you're dealing with a cation, polyatomic cation, then when it comes to the charge, we subtract enough electrons, which would be equal to the number of plus charges, all right? So that's basically how that is done. All right, let me go back to the PowerPoint here and continue our discussion of certain situations where the Lewis structure simply will not follow the molecules of, if you draw a Lewis structure for certain molecules, they won't follow the Lewis structure. There are some situations where you'll have a molecule, you'll end up with an odd number of valence electrons. So therefore, basically one of them will be definitely unpaired. And these structures we call free radicals, all right? One typical behavior of free radicals is that they tend to be very reactive because they need another electron to pair up with the unpaired electron. So they tend to engage in reactions where that is happening. There are some molecules where basically you're going to end up with incomplete octets. In other words, you'll have less than 8 electrons on the outer shell of certain atoms in these structures. Some examples of elements which will engage in this would be beryllium, boron, and aluminum. All right. As a result, again, these these tend to be very reactive. They tend to react in such a way so that they end up after the end of the reaction with a complete octet. In other words, they engage in reactions where they gain electrons. All right. Also, you can have situations where some compound will have more than 8 electrons on its outer shell. What we say in this particular case, the terminology that we use is that we say that these compounds or the molecule or the atoms can expand their valence shells, right? Which is what I was referring to earlier. If you remember, I said that nitrogen and carbon cannot have more than 8 electrons on its outer shell, but there are certain elements that can, and these are elements that belong to period 3 and beyond. Okay, and finally, and that's what basically this statement is right here. The central atom can have expanded valence if it is in the 3rd period or lower. So very important for you to realize that. So we're going to look at a couple of examples where that's the case. So the first example here, let me get to my pen function here, is bromine pentafluoride. So in the case of bromine pentafluoride, each bromine will contribute 7 electrons. Each fluorine will contribute 7 electrons times 5, so that gives you 35. So when you add this up, it gives you a grand total of 42 electrons, all right? So in the case of this molecule, the bromine would be in the middle, and you just surround the fluorines. And it doesn't matter how you arrange it because we're not concerned with the shape. So we start assigning the electrons. So this would be the first pair, 2, 3, 4, 5, then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, this is 21 pairs. So the question now becomes, where will the 21st pair go? And the 21st pair would go on the nitrogen, on the bromine, I'm sorry, like that, all right? So that would be the Lewis structure of this particular molecule. And you'll notice that the boron, let me go back to the pointer here, the boron has more than 8 electrons. In fact, it has 2, 4, 6, 8, 10, 12 electrons on its outer shell. So therefore, boron is one of those situations, where it can have more than 8 electrons because it's in period, if I remember correctly, period 4. Let me check and make sure. Bromine, oh, I said boron, right? It should be bromine. Bromine is in period 5, actually. So 1, 2, 3, 4. Actually, period 4. So bromine can expand its octet so that it ends up with more than 8 electrons on its outer shell. Okay. Let me move on now to another example. Let me just erase all this here and move on to the next example, which is the sulfate ion. And we do like we did before. This time it's a polyatomic ion. So if you remember what we said, we have to add electrons for every, whoops, what did I do? We have to add electrons for every charge. But anyway, before we get to that, so let me start off with the sulfate ion. So sulfur will contribute 6 electrons. Oxygen will contribute 6 each times 4 gives you 24 electrons. And each negative charge will be responsible for 2 additional electrons, so 2 electrons. So basically this gives you a grand total of 32 electrons, which is equal to 16 pairs. All right, then we come over here and we put the sulfur in the middle, surrounded with the oxygens, and then we put the bonding pairs 1, 2, 3, 4, and then the non-bonding pairs around the oxygens 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Then we calculate the formal charges, which I'm going to do down here. The formal charge for the sulfur would be equal to the group number for sulfur, which is 6, minus half the number of bonding electron, which would be 2, 4, 6, 8, so 8 electrons, minus the number of non-bonding electrons, which would be 0, so therefore you're going to end up with 6 minus half of 8, that's plus 2, right? Then in the case of the oxygen, the formal charge would be 6 minus half of 2 minus 6 equal minus 1. So each oxygen is going to carry a minus charge in the structure, and the sulfur carries a plus 2 charge. So basically, in this case, 2 of these negative charges will cancel out the 2 plus charge, and you're going to have the formation of double bonds as shown here. S, double bond, O, double bond, O, single bond O with a minus charge here, single bond O with a minus charge here. And again, this is an example where the central atom has more than 8 electrons, the sulfur. Sulfur has 1, 2, 3, 4, 5, 6 times 2, 12 electrons on its outer shell. So again, this is an example of an expanded octet situation. Okay, let me work the other examples. Let me erase all this here. Okay, let me quench my thirst a bit. Okay, so the next example is sulfur trioxide. So let me go to my pen. So SO3 is the formula. So again, we add up the valence electrons. Sulfur will give us 6. Oxygen will give us 6 each, times 3 equals 18. So that will give you a grand total of 24 electrons, which is equal to 12 pairs. Then we put the sulfur in the middle, surrounded with the oxygens, and then we put the bonding pairs. 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12 of the non-bonding pairs. Again, we calculate the formal charge. So the formal charge would be for, in the case of sulfur, the group number, which is 6 minus half of 6, which is the total number of bonding electrons minus 0. So that would be equal to plus 3. And in the case of oxygen, formal charge of oxygen would be 6 minus half of 2 minus 6 equals minus 1. So we're going to have minus 1 here, minus 1 here, minus 1 here. And down here with the sulfur, you're going to have plus 3. So in this case, basically the charges will cancel out each other, because you have 3 negative charges bonded to an atom with 3 positive charges. So the final answer is going to be S double bond O bond O. And that's it. All right. So that's the, and again, sulfur here in the middle has a total of 2, 4, 6, 8, 10, 12 electrons on its outer shell. So again, sulfur is expanding its octet. Okay, the last example I'm going to work here. Oops. So that would be PO4 3 minus. Okay, so phosphorus will contribute 5 electrons, and each oxygen will contribute 6 times 4. That gives you 32. And then we have a -3 charge. So therefore, we add 3 electrons, right? So that gives you a total of 37 plus 3, 40 electrons, which is equal to 20 pairs. So we come up here, we put the phosphorus in the middle, surrounded with the oxygens, and then we put the bonding pairs, 1, 2, 3, 4, then the non-bonding pairs, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I made a mistake. What's a mistake I made? 4 times 6 is 24, not 32. What am I thinking? Okay, so this is going to be wrong. It's going to be 27 plus 5, 32 electrons equal to 16 pairs. Okay, so let me correct that. So basically, we have assigned all 16 pairs. All right, so the formal charges. So formal charge, formal charge starting off with phosphorus, that'll be equal to the group number, which is 5 minus half of 8 minus 0. So that will give you +1. And the formal charge of oxygen is 6 minus half of 2 minus 6 equals -1. So basically in this structure, we're going to have a situation where the phosphorus has a +1 charge and each oxygen has a -1 charge. So in this particular case, you can move just one pair of electrons to form a double bond like that. And therefore, the final structure is going to be O minus here, bonded to P, bonded to O minus here, double bond O here, O minus here. And that would be the final answer here for the phosphate ion. All right, so I think I've given you enough examples so that you get a good picture and a feel for how to draw the Lewis structures based on the formula given. All right. Okay. So for this video, until next time.